Hello students. Last day we discussed about chemical shift and anisotropic effect in NMR spectroscopy, and you know the difference in the absorption position of a particular proton from the absorption position of a reference proton is called the chemical shift of this particular proton. So today we start our lesson from anisotropic effect. Though in the previous video I discussed about this anisotropic effect, but it is very important for NMR spectroscopy, so I repeat it again. We can explain the anisotropic effect in NMR spectroscopy by taking some examples such as alkene, alkyne, aromatic ring system, carbonyl group, or cyclohexane. So let us begin with alkene molecule. In case of alkene molecule, it is planar in nature due to the formation of pi bond by the parallel overlap of p orbitals, and under the influence of a external magnetic field, the pi electrons of this alkene molecule are circulate, and due to this circulation of pi electrons, it generate a secondary induced magnetic field, and this induced magnetic field may be aligned with the applied magnetic field or opposed with the applied magnetic field. If you notice this is an alkene molecule, and in case of alkene, these pi electrons are circulate in presence of external magnetic field, and the circulation going on over clockwise, and the molecule present perpendicular direction with the applied magnetic field. When these pi electrons circulate, then it generate a induced magnetic field, which is shown in this figure, and this induced magnetic field create paramagnetic region or diamagnetic region. If you notice this direction, which is paramagnetic with this applied magnetic field, which may be shown by this, and this region which is diamagnetic with the applied magnetic field. When the induced magnetic field is paramagnetic, this is paramagnetic, then the precessional frequency or effective precessional frequency increases for the proton. I can explain this with the help of this figure. When the pi electrons of alkene molecule are circulate in presence of external magnetic field, this generate a induced magnetic field, and this region which is parallel with the applied magnetic field, or this region which is parallel with the applied magnetic field, and del x equal to nu x minus nu TMS divided by nu 0, where the nu x is the effective frequency or precessional frequency, which is field by the protons. So when the induced magnetic field is parallel with the external magnetic field, then this mu effective value increases, and we notice this del x value is directly proportional with this effective precessional frequency, and with the increasing of this nu, the del x value increases. So proton which is present in this region are show higher del value in NMR spectroscopy. But if any proton comes into this region, which is diamagnetic with the applied magnetic field, then the precessional frequency or effective precessional frequency decreases and del value decreases. So proton, if come over this double bond, then the precessional frequency decreases and it will show lower del value. You know, in case of alpha pinene, here present three types of hydrogen, where this hydrogen show del value at 1.63 in NMR spectroscopy, but this hydrogen show a del value of 0.83 in NMR spectroscopy. So how can you explain this observation? If you notice, this hydrogen or this methyl group present at the over of this double bond. So we can explain by this way. This is a double bond, and in presence of external magnetic field, the pi electrons circulate and it present or it produce a induced magnetic field. So this hydrogen present at the top of this region, which is diamagnetic with the external magnetic field B0. That's why the precessional frequency or the nu x value decreases and it show lower del value in NMR spectroscopy. In case of carbonyl group, the picture is same, because here also present a pi bond, that is pi electron. So under the influence of external magnetic field, this pi electron circulate, and during circulation it produce a external magnetic field just like this. When this pi electron circulate, this produce a induced magnetic field same as alkene molecule, and this hydrogen again comes into the parallel region, which is known as deshielding region also. Deshielding. So due to this parallel region, the effective nu value or effective precessional frequency of this hydrogen increases, as well as this aldehyde hydrogen comes into the higher del value in NMR spectroscopy. In case of acetylene, if you notice that the acetylenic hydrogen show del value at lower position, such as 2 to 3 ppm. So this observation we can also explain by this anisotropic effect. You know, acetylene molecule is a linear in structure. Therefore, the structure just like this, and this is the pi electron. So under the influence of external magnetic field, this pi electron circulate, and during circulation it produce a induced magnetic field. So we notice this, that this hydrogen present into the shielding region. This hydrogen present into the shielding region. Therefore, the magnetic field which is generated due to external magnet oppose this magnetic field, and therefore the precessional frequency of this hydrogen decreases and comes into the resonance lower del value in NMR spectroscopy. Therefore, the acetylenic hydrogen show lower del value in NMR spectroscopy. For aromatic molecules, especially for benzene or others aromatic compound, show their del value in NMR spectroscopy at deshielding region or at higher region. So how can we explain this fact? If you notice that this is an benzene molecule which is planar in nature, and all the p orbital are parallel with each other. So in presence of a external magnetic field, this p electron cloud circulate, and during this circulation it generate an induced magnetic field. Therefore, this hydrogen, which is a aromatic hydrogen, comes into the deshielding region, which is parallel with the external magnetic field. Therefore, the nu x value of the aromatic hydrogen increases, and it show a deshielding value in NMR spectroscopy or higher range value in NMR spectroscopy. In contrast with the striking anisotropic effects of circulating pi electrons, the sigma electrons of a carbon-carbon single bond produce a small effect. For example, in case of cyclohexane, the axis of the CC bond, in cyclohexane is the axis of deshielding cone. This is a deshielding cone, and this hydrogen comes into the deshielding region, and this hydrogen comes into the shielding region. As this hydrogen comes into deshielding region, therefore it show higher del value in NMR spectroscopy. But this hydrogen present into the shielding region, and therefore it show lower del value in NMR spectroscopy. The examples of anisotropic effect is quite interesting. In presence of aniline system, if you notice, there are two type of hydrogen present in the aniline system. So a aniline system just act like a aromatic system, and under the influence of external magnetic field, this pi electron circulate, and during circulation it also produce a induced magnetic field. And if you notice that this hydrogen again comes into the deshielding region, therefore this hydrogen comes into the higher del value in NMR spectroscopy. But this hydrogen, in case of this hydrogen, if you notice this magnetic field are diamagnetic with this external magnetic field. So this hydrogen, we can say, comes into the shielding region, therefore it show lower del value in NMR spectroscopy. In case of this type of molecule, if you notice this this methyl proton comes into the shielding region in NMR spectroscopy and show very low value in NMR. So if you notice that this CH3 molecule comes into the shielding region in aromatic ring system. If you consider this is an aromatic ring, so just like this is an aromatic ring, and during circulation of pi electron it generates a induced magnetic field, and this methyl group comes in this region. Therefore the precessional frequency or effective precessional frequency due to the opposite magnetic field decreases and show very low del value in NMR. So this is anisotropic effect in NMR spectroscopy. I think this video may helpful for you, and if you have any questions then follow the NMR spectroscopic book and ask me if you have any inquiries. Okay, thank you.